On the next page, we're going to do some more graphing here in polar coordinates. The first example is just talking about getting things into polar mode, and we've already seen that on Desmos. We can also do it on the calculator. You can't go in between the two forms as easy in the calculator. Actually, I have to switch the mode down from function to polar, and then it's one or the other. You can't do polar and polar and rectangular at the same time like you can in Desmos. So you could switch it into polar, and then if you do that, you'll notice that your y equals is not a y equals button anymore. It's now r equals, because equations need to be solved for r. They also, like I said, need to be solved for r, so you could not graph them implicitly on the calculator like you can on Desmos. So we'll probably stick to Desmos for graphing. And then the first example here is just asking us to regraph some of them on the previous page. We already did that, so let's move on to the bottom. We did that in the previous video. So what we want to do is start by making a prediction. This is like a by hand prediction of what this graph will look like. All right, and so let's see. The first one, r equals 3. So it's got a constant radius, and the angle is going to vary all the way around. So this is going to be a circle, and it's going to be a circle with radius 3. So 1, 2, 3. See if we can get our circle sketched out here real quick. It should just be the circle that goes with the radius 3 all the way around. That's what the graph should look like. We should be able to get that by verifying it on Desmos as well, by just graphing r equals 3, and there's our circle with the radius 3 on that third concentric circle line. All right, and the next one, we need to graph r equals 5 times the sine of theta. So I'm going to start by thinking about this, what this might look like. And so on the unit circle, when I think about what the sine values look like, and so the sine values, this point over here is 1, 0. So the sine value is 0. And then up here it is 0, 1, so the sine value is 1. And then it's going to vary between them, and it's the y-coordinate that we're looking at. So the sine value on the unit circle is the y-coordinate. So we're looking at various increasing y values to get those sine values. Okay. So I'm going to start off with, when I have a very small angle for theta, we're going to be right at the origin still. Then as that angle gets larger, so as the angle, looking at, let me draw some concentric circles right here. I'm going to make them light. Concentric circles for my polar graph. So 2, they're not anywhere near the same size, so that's not good. Sorry, I'm drawing. There we go. And then our fifth one. Okay, so pretending that I had skill enough to draw up concentric circles here. So we would start on a small angle. So we've got our little radial lines too. We'll try to dash out some radial lines. Alright, not beautiful, but it's okay. On a very small angle, and I could do actual angles to confirm, but on a very small angle, I would have a very small number times the 5. So it's going to be something relatively small. As I get bigger, it's going to get larger, and when I actually get to 5, it's going to be 1 times 5 is 5. So I'm picturing it doing something like this. And then on the other side, see, as I allow my angle to rotate back around, the y values get smaller, and back over here, it turns them back into 0, -1, 0. So I have to go back to that same point. So they're going to have that reverse pattern. Okay, so that deals with angles that rotate through the top half of the circle. What's going to happen down here? And what's going to happen down here is that these are going to have negative outputs down here. Sine is positive on the top and it's negative on the bottom. So if I have negative on the bottom, for my angles that are negative, my radius is going to be negative. And so it's going to flip them and go right back around. So I actually won't see anything down here, because for angles that are below the x-axis, the output of this is going to be negative, and so my radius is negative, and so I flip across the to one of the co-angles. I flip across the origin, and I use the positive angle with the positive radius again. So I'm actually expecting my picture to be something like this. Now, with my grid off, it may actually be a circle instead of an oval. Let's take a look at how Desmos is going to graph that one. So this one would be r equals 5 sine theta. Yeah, it looks very circular when they've graphed it, and again, my graph was an approximation, so it should have been a circle, not my little oval. But we had the right idea about what it should look like. It's a circle that touches the x-axis and touches up there at the top at 0,5, and then makes a perfect circle around. Interesting. Okay, so that's actually an easier way to write the equation in polar than it is in rectangular. Rectangular would involve, it would not be a function for sure, and it is a function right here in polar. All right, let's look at the last one. So I don't think about cosecant as efficiently as I think about sine and cosine, so I would rewrite this one. So the first thing I would do is r equals 2, reciprocal function, cosecant there, for 2 over sine of theta. Then, if I multiply that over to the other side, that's r sine theta equals 2. And I know that that's y equals 2. So I actually am converting it into polar to figure out what it looks like. That might be cheating. But y equals 2 is a horizontal line. That would be what this graph is going to look like. Alright, so if we graph this one again over here, I can change this into r equals 2 cosecant theta. And yep, we can see it's the horizontal line that would hit where y is equal to 2. It's the equivalent of y equals 2 in rectangular. So this is a case where I think that it's more difficult to visualize this one in terms of polar than it is in terms of rectangular. Okay, and on our last page here, some types of polar graphs are so interesting and lovely that they have their own names. So there are some cartoids. So I'm going to graph these on decimals, and I probably won't draw the example graph. You can draw them, but let's just take a look at each of these. So the first one, we have those cartoids, and those are the heart graphs. And so if you have something of the form r equals 1 minus sine of theta, you got that little heart shape, and you can vary those cartoids by changing some of the properties. So changing, that one has a bigger loop, and you put the 2 in front of it. We could do some other transformations. That's not a quartoid anymore at all. If you put it in there, we can change things. That's making it too big. So again, there are a variety of things that we can do to affect the way this graph might look. Make a cartoid. That one blurs it out a little bit. So anyway, that family of graphs is called a cartoid. The cissoid is of the form r equals sine theta times tangent theta. Do I need to type in the times? I wonder if I didn't like it, so I'm going to just stop it and try it again. So r equals sine, I'm going to put some parentheses so it makes sure that I know what's inside the sine of theta, times tangent of theta. I think what happened before was that it wasn't sure if since I didn't use parentheses, if it was my tangent theta was inside the sine or not. It was just not defined well enough. Okay, so this is the cissoid, and it's an interesting shape. It's not something I can draw well in rectangular, we'll just put it that way. So it swishes up and swishes down like that. So an interesting shape. Another interesting shape we could look at is r equals 3 theta. This is called the Spiral of Archimedes. I can't see it spiraling until I zoom out. And there we go. We can start to see the spiral forming. Okay. It doesn't really stop right here, by the way. The only reason it's stopping is because I have a maximum value put in on my axes for it to go on. Now, Decimals does not let me choose the highest theta value to spin around. It's defined based on the x and the y, but if I incremented those up, it should change it as well. But it might have the theta value fixed because it's not letting me change the theta. Yeah, it might just have that theta value fixed. Okay. So, if you go on a calculator, you can get it to actually change how many thetas you're going to see. So that's the Spiral of Archimedes. Okay. Okay, and then the next type of graph, we have an r equals e to the theta over 10. And this is a logarithmic spiral. So this spiral is spiraling down in, unlike Archimedes spiral, which is spiraling out. So this one, if I zoom in, it's going to reveal more of the spiral. Looks like a nice little clamshell from that. If I reflect it across the y-axis, I've got myself a nice little clamshell. This would be fun to use in your Decimals project and then like add some more parts to it. Especially if you convert it back into grid and then add some more parts to it. So, you know, adding a polar graph into your Decimals project would be really sweet. Okay. Then, let's see, we can also graph, that one's the logarithmic spiral. We can graph the next one, I don't know how to pronounce it, but like strophoid. So r equals cosine 2 theta. I think I'm going to do parentheses around this one or have the same problem I had before, times the secant of theta. Oh, my equal sign didn't type right. There we go. Okay, so this one is something similar to the cissoid, except that it's got a little swirl right there, which the other one did not. So that's kind of pretty. And I can graph the others, or I'll let you graph the others. So I'm not going to graph the last three. You try them. And then there's a note at the bottom. Why are polar coordinates useful for mobile phone companies and radar operators? Well, radar, I think it should be obvious because we want to talk about rotational. But what do you think about mobile phone companies? Why they would be important there? Let me know.